Hello, my name is Mitchell Hallett, and today I will be presenting my artificial blood vessel design project. I will be covering the research, the materials, the SOLIDWORKS modeling, flow simulations, and the final recommended graft design. Alright, so project objective. The goal of this project was to design a realistic artificial blood vessel, identify 3 biocompatible materials, then to build a SOLIDWORKS model in multiple lengths, finally to simulate blood flow under normal and extreme conditions, and then to choose the best overall option. So, why the blood vessel design is so important. Artificial vessels must survive human blood pressure. This is very crucial. They have to be stable under repeated cyclic loading, and they need to be good in long-term biological exposure scenarios. And they also need to be economically feasible to manufacture at a large scale to the masses. Okay, now let's go ahead and take a look at the physiologic flow rates. From my research, clinical literature shows about adult cardiac output around 5 liters per minute. For safety reasons and just general good practice, I modeled both a normal flow at 4 liters per minute and a worst case scenario, which is 5 times higher. Alright, so now let's go ahead and take a look at the vessel size selection. So typically aortic graft sizes can fall between 22 and 28 millimeters. So I just opted for a 25 millimeter inner diameter. I felt like that was a safe bet. And I went with a 2 millimeter wall thickness to match a pretty realistic surgical graft. Alright, so now we're going to go ahead on to materials evaluated. So the ones that I went ahead and looked at is I compared PET, polyurethane, and magnesium alloy AZ31. These were evaluated based on strength, cost, corrosion resistance, and clinical biocompatibility. I felt like these were the strongest factors that would impact a product of this material type and functionality. Okay, so let's go ahead and look at the material properties. Essentially, this is going to be the overall results that I found from my research, comparing all of the properties for everything. Essentially what I found is that magnesium is the strongest, but it corrodes quickly, so that's an important factor to be considered in. And then I found that PET and polyurethane have proven medical use, and they've got a wide range of usage in real life scenarios. I also found that PET offers the lowest cost, which becomes a very important factor when you're scaling production for high production products. Alright, so here is the SOLIDWORKS modeling slide. So essentially what I did is I created a model vessel at 3 lengths for each material. This gave 9 unique models that I ran twice, so it was 18 total simulations. It was a pretty basic simulation, but there was a lot of variations between the simulations, and they all used the same diameter and wall thickness. Okay, so here's how I went about setting up my CFD. For the simulations, blood density and viscosity were applied to the fluid. I used flow rate boundaries at the inlet and static pressure at the outlet. This is pretty standard of flow through a cylindrical hollow shape, and then laminar flow was appropriate due to the large vessel diameter. Alright, so here's basically what I found from the CFD. I found that the shear stress increased as vessel length increased. But even in the worst case flow scenario, stresses stayed far below all of the material strength limits. All materials were essentially structurally safe, this means. Okay, so here's going to be my final recommendation after all of the testing and the research. I'm going to go ahead and say that PET is the best overall option. It has decades of successful medical use. It's got really excellent strength. It's low cost, and it's got consistent performance across pretty much every simulation that I ran. Polyurethane is an acceptable but less cost efficient option, and then magnesium was eliminated due to its corrosion and cost, so that was just not a viable option. Okay, so here are kind of the key takeaways, the big things that I learned from this project. first and foremost, I found that PET was the most balanced and practical choice. That was kind of the main objective of the report. As far as things that I learned, I learned that accurate physiological inputs are critical for proper design. I found out how important CFD is and how powerful of a tool it is. As far as future improvements, I would include a pulsatile flow, which is essentially just the heartbeat pulsing, so it's not a steady stream, but it's got pulsing pressures and imbalances in the flow. And then a structural FEA would also help a lot.